In this video, I'm going to discuss logical design, so logical database design. When we talk about database design in general, there's usually two types of design we do. There's logical design, which is when we design our needs for how we're going to store data in a database without respect to the relational database management system. In other words, it doesn't matter if it's Oracle or MySQL or PostgreSQL. We don't care what the RDBMS is going to be. We're going to make our design irrespective of that. We don't really care about what type of system we're doing. So it's regardless of the RDBMS. We don't care about the limitations of any particular database management system. We don't care about the features or anything like that. We try to put all that stuff aside and concentrate more on what our data needs are. What are the things that we have to store? How are they related to each other? That's really what we're concentrating on in logical design. Later on, once you finish a logical design, you might move to a physical design. And in physical design, that's where we take our logical design and we adapt it for whatever particular database management system we're using. So at that point, we can start thinking about the limitations of certain DBMSs, certain things that they can't do, that we don't care about in a logical design. And we can also think about some advantages of certain database management systems, certain things they can do that maybe we didn't have to think about in the logical design. In this video, I'm going to use some vernacular that I'd like you to be familiar with. So in logical design, we typically use the terms entity and attribute. But later on, when we move to physical design, which some of you may already be familiar with, the term entity would become table. So we call it a table in physical design. That's our table in the database, for example. And an attribute is really a column or a field in that table. And a collection of records or rows can form that table. In the theoretical realm, which in some database classes you go into database theory, they'll probably talk about tables as being relations. So you may have heard that term. I use the same term, attribute, and a tuple is a collection of records. So I just want you to be familiar with those terms. Again, I'm going to use the terms entity and attribute since we're talking about logical database design in this particular video. So in order to show a logical design, one of the tools that we use to do that is an entity relationship diagram or an ER diagram. I'm not going to talk to you about how to use any specific tools to create these diagrams. Microsoft Visio is one popular tool from Microsoft. There are many others out there, and I have a video which shows you how to use Microsoft Visio to create the diagrams that I discuss in this video. So an ER diagram is basically a standard method to diagram entities, their relationships, and the attributes. Sometimes you'll hear me call it a modeling technique. The term modeling technique is borrowed from UML. Certainly, if you're interested in UML, you can go take a look at that as well. And I do have some videos that discuss UML. UML has a diagram called class diagrams, which is very similar to what we do with an ER diagram. The syntax is a little bit different. The focus is a little bit different. But there are things that are very similar about that. So I certainly encourage you to take a look at UML and be familiar with it. You'll certainly see it in the industry quite a bit. But ER diagrams are also quite common. In fact, in many projects, I've seen both class diagrams and ER diagrams. The class diagrams may be more geared towards the software design, whereas the ER diagrams are more geared towards the database design. And they have their strengths and their weaknesses in both realms. But in this video, I'm going to talk mostly about logical database design, so we're going to use ER diagrams. They certainly lend very well. Prior to creating an ER diagram, a few things should have been completed. You should have done some analysis about your needs for this database. You would have identified nouns. So in your analysis, you may have done interviews. You may have collected artifacts such as business documents. You may have looked at standard operating procedures. You may have done some questionnaires. There's various ways that you would gather all the information about what the system needs to do and what the database needs to store. You would have picked from that your nouns, which is a person, place, or thing. You would have grouped those nouns into common themes. So you would find groups of nouns, group it into common themes. Those common themes that you identify become our entities or our tables in our database. Other nouns would become the attributes which describe those common themes. So you have a major topic, which is our common theme, and then you have nouns that describe those. So you're sort of subdividing which nouns describe something and which ones are something that we are actually going to keep track of in the database. Some of the nouns will uniquely identify a specific instance of an entity. In some cases, it may be a collection of nouns that describe something, and in some cases, a single noun may describe an entire record. In most cases, you want to try to find something that's going to primarily identify or uniquely identify any single instance of an entity. And we'll call that a primary key. And we probably talked about in other videos about primary keys and what they are. And I'll touch on that a little bit again in this video. So what exactly is an entity? As I discussed, an entity is that person, place, or thing that we have to keep track of in our database. Once you know what all of your primary entities are going to be, or the major topics you've identified, we have to diagram those. The way you diagram an entity is you draw a box. And in the top of that box, you're going to have the name of the entity's name. And that will eventually become our table name in a physical design. Below that, in the bottom of the box, you're going to have attributes. So you're going to list the attributes one on top of the other, just as you see here. In addition, one of those attributes that you've identified is going to be the primary key. It gets a special place in the diagram, so it gets its own slot underneath the entity name. If you have multiple fields or multiple attributes that make up a primary key, you would list all of them in that top section. It's typical to underline those, and in many cases, in some tools, you'll have the ability to have this extra little area on the left where you can identify which are primary keys and foreign keys. Now, in logical design, we're not worried about foreign keys yet, although I'll talk about those so you understand the concept. But in many cases, when you label something as a primary key, it'll give you the little identifier PK next to it in that area off to the left-hand side. But again, it's typical in some drawing tools to underline and put PK next to it. And sometimes the PK is off by itself in that left-hand side in that box. I know in Microsoft Visio, it'll look very similar to this, but in other drawing tools, it may look a little bit different. The important thing is we should be able to easily identify which of the attributes is a primary and a foreign key. We should be able to easily figure out what the entity's name is, and we should see a list of all of those attributes. So these are the four basic parts of an entity in an entity relationship diagram. There are different types of entities. So these are just a few types of entities. A domain entity is any entity that describes the core business or something that to which we're trying to solve the problem with this database. So for example, in a customer relationship system, the customer would be a domain entity. Their phone number may be a domain entity, for example. Linking is when we use extra tables or extra entities to connect other entities together. And you'll see that later on. We usually do that when we get to more into the design, the physical design, that is. Lookups can be for lookup values to ensure data integrity. For example, if you have maybe patients, you can have male or female. So you might have a lookup to make sure you're putting in valid values for that. It could be maybe male, female, or other, or something like that. And then you have weak entities which depend on another entity for its meaning. For example, the phone number doesn't really mean anything unless it's attached to some other object like a person or a customer or an employee and so forth and so on. So that might be an example of a weak entity. Let's not worry too much about those types for right now. The important thing is once we have our blocks with all of our entities, and as I said before, we're going to start with the entity name. We're going to list all of our attributes, and one of those attributes is going to be something like, in this case, the ISBN is the primary key for a book. So this might be a database that's going to contain books. Now, the books, as you know, would probably have an author, right? So most books have an author, and we might have a primary key. In this case, I made one up called author key. So these two tables or these two entities have a relationship to one another. And to show that relationship, I would draw a line between the two. Now, I didn't talk about foreign keys, but when we get to design, we're going to talk more about foreign keys. So a foreign key is how we relate to another table. And again, we'll talk more about that in the design. I just wanted to show you real quick that typically you would also see in these diagrams the foreign key. I also want to mention too that if you look at the ISBN, we talked about this before, that primary key would be a natural key. So that's a good example of a natural key. If you recall from earlier, when we talked about in an earlier video, we would have talked about the different types of primary keys. So a natural key is one that we didn't make up. So anytime you have an attribute that we don't make up, but yet uniquely identifies an entity, that's a natural key. On the other hand, the other table, I made up that key, author key. So I made that up. That's the primary key. It's uniquely identifies an author, but there isn't anything inherently unique about an author, so I had to make something up. So that is a surrogate key. So it's a good example of a surrogate key. Now, there are several different ways to show the relationship between different entities. And I'm going to talk about I'll talk sort of about three notation styles, different types of notations you can use. The simplest is the arrowhead notation, and that's simply where you draw a line from the primary table to the foreign table. So you can see in this example, a book has an author. So my arrow points to the author. In other words, the foreign key points to the primary key and author. And that's why I wanted to show the foreign key in this particular diagram. So you can see that eventually the foreign keys would be in that left-hand side table in this example, and it would point to a primary key in another table. So the arrowhead notation is okay. It doesn't give us a lot of information about cardinality, which I'm going to talk about in just a minute. But the other notation we can use is crow's foot. This is a pretty common notation in ER diagrams, and it's used in Microsoft Visio. So if you're going to use Microsoft Visio, you'll see the crow's foot notation. It's, when you go to create your diagram in Visio, that'll be one of the options, the crow's foot notation. And this one has several different symbols. So when you look at crow's foot, the circle means 0, the straight line is going to mean 1, and the crow's foot means many. And you'll know what this means in a little bit. We're going to talk about this in more detail. But that refers to the cardinality. So when we talk about cardinality, that is the degree to which different entities are related, or the numbers of things that can be related to the number of things on the other side. I'll show you an example. So here we have a book on the left. A book has one and only one author, for an example. So I would show the symbol, and you can see I've added the symbol on the right-hand side of our relationship line. I added a symbol that has one and only one. So I would read it as the book, which is on the left, and then I would look at the relationship symbol, or the notation, in this case the crow's foot notation, on the right-hand side as it connects to author. So I'm reading a book as it connects to author. So a book has one and only one author. Then I would read the other way. So it started author, and I might say that an author has one or more books. So an author can write one or many books, or one or more books. However, a book can have one and only one author. Now, some of you may be saying, Brian, wait a second. Books can have many different authors. You can have a couple different authors of a book. And yes, that's absolutely true. You could. So in many cases, there's lots of different ways that you can interpret the cardinality, or how tables relate, or how entities relate to one another. But in many cases, we can look to the business rules that we discovered in the analysis phase. So when we do our requirements gathering and our analysis, those business rules that we turn up may help us determine what the correct cardinality is. So in this particular case, perhaps there's a business rule that I can only have one author per book. It'd be a strange business rule, but if that's a business rule, we would express that in the database and in our logical design by showing that business rule. So again, you can look at those business rules to kind of determine what that cardinality should be. If it's not determined in the business rules, then you have to use your best judgment to figure out what that cardinality would be. So this is an example of the cardinality between book and author. Some cases, as you can see here, we have repeating fields in an entity, and this is not good. So typically when you see repeating fields, and you can see in this case, I have subject 1, subject 2, subject 3. Anytime you see a number on the end of an attribute, that's usually not a good thing. There's usually a hidden attribute in there. So in this case, we're going to take any repeating fields that we see like this, and you can create a new entity for that. So in this case, I move the subjects into a new entity. And for example, I could show that a book can have 1 to 3 subjects, and a subject can appear in 0 or many books. So that's a different notation style. This is more like a class diagram you might find in UML, but it is also a notation style that you could use. It's an alternative to the crow's foot, and again, it can be used in Microsoft Visio. So this could also be, I kind of like this notation because it has a little bit more information than the crow's foot. So in the crow's foot, for example, I couldn't show the exact minimum and maximum cardinality. I couldn't say how many maximum records there could be or minimum records. But with this notation, I can. I can use an integer to show exactly how many records I can have. So when I read this, I would say a book can have 1 to 3 subjects, and a subject can have 0 to many books. And if you think about it, that's a business rule that might make sense. If you go to the library back in the old days with the card catalogs, most books could only have 3 subjects. So you had 3 primary subject areas, and they would put, a card for each subject area in the card catalog. So if you're looking up by subject. Now, of course, today, most cataloging systems can support far more than 3 subjects, but that could be a business rule that we could express with this type of notation. Now, we haven't normalized this yet, but what we've kind of done here is taken a first step towards normalization. I'm going to talk more about normalization in a later video. I don't want you to think if you're familiar with normalization, don't think that you have to start normalizing during the logical design. We're going to talk about that later on. Again, we want to separate that physical design from the logical design. We're really just trying to think about the entities and how they relate to one another during the logical design. And then we'll move to the next step in the physical design where we start to normalize that database. So don't worry too much about normalization yet. One-to-one relationship. We have a couple different types of relationships. So a one-to-one relationship is a relationship where for each record in the primary key table, there is no more than one related record in the foreign key table. So typically a one-to-one can be either exactly one on one side to exactly one on the other side, or it could be one on one side to 0 or 1 on the other side. So it could be optional to 1. So it doesn't have to be exactly 1. Sometimes it's none or 1. But the point is there's never many. You can never have many of anything on either side. It's always a one-to-one match on each side. So there's a couple different examples, but you won't see one-to-one relationships very often. Many of you, when you create an ER diagram, you may not see any one-to-one relationships because they're not commonly used. But one way you could use them is to obviate the need to store null values in a table. Another place that we see them sometimes is for security, to segregate different parts of information about a single entity if you need to store it in 2 different places. So null, just so you know, means nothing. We haven't talked about the term null in these videos yet, but a null basically means that there's nothing there. It's the absence of any data. It doesn't mean 0. So some students will say, well, null must mean a 0, but that's not exactly true. 0 is a number, but a null is literally nothing is there at all, not even a 0. Why do we not want to store nulls? Nulls can ruin your day in databases. We'll talk about why later on, but it's generally best practice. If you can avoid putting nulls in your database, it's a good idea to avoid that. So a one-to-one relationship gives us a way to do that. Let me show you what I mean. Take, for example, our books. Now, a typical bookstore like Barnes & Noble or something like that, they don't just sell books. They also sell music, and they sell magazines, and they sell movies, and so forth and so on. So maybe instead of having a table called books, I have a table called media, and it could describe any one of those things that we sell. So I have a primary key here. I've changed it to media key instead of the ISBN because now it's not a book. It may not necessarily have an ISBN. So I have to create my surrogate key. I have a title, format, release date, publisher, ISBN, issue, volume, and so forth. Now, if you think about it, if this were my table, these are what the values of that table would look like. So, for example, the first record is a book. It only has a publisher and an ISBN. Books don't typically have issues and volumes. They don't always, and of course, format and release date might not apply to a book either. However, format and release date would apply to a movie. So Rocky is a movie. I might sell a format that is Blu-ray that was released on 11/21/1976. And likewise, I could sell magazines. And a magazine maybe wouldn't have an ISBN number. It maybe wouldn't have a format, but it would definitely have an issue and a volume number. So different things are important to me in different ways for this particular entity. So maybe I don't really have a single entity here. I have an entity with some weak relationships. And I'll show you what I mean. So all media, regardless, will always have a title. So I can leave the title in my media entity. However, I could take the format and release date, which I know are typically for movies or videos, and I can move that to a new table called video. Then I'll take publisher and ISBN, which I know are usually for books, and move that to a book table. And I'll take my issue and volume, which are typically for magazines, and move it to a magazine table. So now this is what my database will look like. And when I store data, it's going to look more like this. Notice there are no nulls now because my title exists in the media entity. And then I have an entity each for these different types of media. So I don't have to store all those null values that you see at the bottom. It doesn't really save us on any storage space. We'd really be using about the same amount of storage. So some students will say, oh, maybe this will save space, but not so much. But what it does is it relieves the need for us to store nulls in our database, so it makes it much cleaner. It's generally best practice to avoid those nulls. So that's one use of a one-to-one. And if I were going to diagram that, it might look like this. So my media can have one video, zero or many videos, zero or many books, zero or many magazines. A magazine can be in zero or one media. And really that 0 to 1 probably should be a 1 to 1. So all magazines should have one and only one media. All books should have one and only one media, and so forth and so on. So I could certainly make that change, this diagram. It's a minor error here, but that's roughly what one of these ER diagrams, what it would look like if we had some one-to-one relationships. So another use of a one-to-one is for security. Take, for example, if I had an employee table. Everyone should be able to look up an employee's last name and a first name, and maybe some other details like their email address or phone number and so forth and so on. However, two attributes about an employee that I would not want everybody to have access to would be social security number and salary. But that entity, when we do our initial run through the analysis, that entity has these attributes. Those are all unique attributes about an employee. An employee doesn't have multiple salaries. They don't have multiple SSNs. So they all apply uniquely to that employee. But I want to separate that for security reasons. So you can move that to another table. So it would look something like this. So every employee would have one and only one employee payroll record. And an employee payroll record always relates back to one and only one employee. One thing I want to mention about what I've showed you here with the one-to-one relationships is in many cases, these decisions to go to one-to-one relationships are being made in the database design, not necessarily in the logical design. So I'm thinking, for example, with security, I'm thinking about the limitation that most database engines do not allow you to limit access to only certain columns. You can only do that at the table level, or at least it's only feasible to do it at the table level for a large database. So it becomes easier to separate that data. So that might be the real reason for doing this, but in reality, it's okay if it's all in one table in my logical design. Same with the other scenario for the one-to-one relationship. When we have null values, that might be a database limitation that certain functions break when you have null values. So it's best practice not to do that. So that's a decision we would probably make in the design phase. But I just want you to understand why we might have a one-to-one relationship. A lot of students, when they look at logical design, they say, I must be doing something wrong because I don't have any one-to-one relationships. And that's simply not true. It's going to be pretty common for many of you when you do an ER diagram to not have one-to-one relationships. They're not very common. Now, one that is very common is a one-to-many relationship. You'll have a lot of one-to-many relationships. They are by far the most common relationship between tables, or between entities, I really should say, in most ER diagrams and in most databases in general. For each record in the parent, there can be 0 to many or infinite records in the child. So if you look at my example at the bottom, an employee can exist in one or many departments, and a department can contain 0 or 1 employee. And that crow's foot notation shows you that in that little diagram. And again, this is the most common relationship you're going to see, is a one-to-many. Now, one thing you might run into when you do these types of relationships, these one-to-many, some students have the tendency to think, well, an employee can be in one or many departments, and a department can have 0 or 1 employee, but also a employee can have 0 or 1 department, and a department can have 0 or many employees. So they might look at it two different ways, and people will get confused because they're looking at it in two different directions. But you can't do that. And if you do think that it's possible that the department, that this could happen, and you were to design it like this, if in your logical database diagram, what you end up with is a stalemate. There's no way to have this type of relationship because an employee can't be in a department until a department has employees, right? So I can't create my department if it doesn't have any employees, and I can't create my employee if they don't have a department. So you get into this stalemate situation, you're just going around and around the board. So if you do see a relationship like this, typically it means what you actually have is a many-to-many relationship, which is okay. You can have many-to-many relationships. So if you find yourself in this conundrum where you've got many things on both sides and you're trying to force it into a one-to-many relationship, instead what you probably have is this, a many-to-many relationship. And in fact, this is probably what an employee and department relationship would look like, because employees can be in one or many departments, and departments can have zero or many employees. And of course, this all depends on the business rules, but assuming the business rules support this, you might have a diagram that looks like this. So one-to-many, you can have each record in the primary entity can have many related records in any related entity. There really is no primary entity here. They're both primary entities because they both can have many records in the peer, in the related entity. The thing about these many-to-many relationships is they can be shown in our logical design, but later on when you do a physical design, you're going to have to get rid of these many-to-many relationships. You're going to have to find a way to correct this so that you don't have it. There is no database management system that can support, or at least not any relational database management systems that can support a many-to-many relationship. So you won't be able to have this later on in your physical design, and you wouldn't be able to codify this into any kind of code to build a SQL database. You wouldn't be able to build a relational database if this is the relationship. However, in your logical design, it is valid to have this. So it is okay in the logical design. But when we step into the physical design, we're going to do some things to make sure that this doesn't happen. The other thing I want to mention real quick in our physical design is we would also be adding our foreign keys. So we would start to think about those foreign keys, and we would use that logical design to determine where those foreign keys are going to go and what they're going to be. So I'll talk about that later on when we talk about the physical design. There are some advantages to using naming conventions. So now that we know how to create these diagrams, when you're putting things in the diagram, when you're labeling things, it's important to use some kind of consistent naming conventions as you do this. So entities or tables, they're typically named with single nouns. It's, a lot of folks have the tendency to want to call a book table books because it's going to contain lots of books. But most people tend to use singular nouns when they name an entity. So it's a good idea to be consistent and use that. It's kind of an industry standard. Although, at the end of the day, is it going to break anything to use a non-singular noun? Of course not. Everything will work fine. But as a matter of convention, usually that's how it's done. Attribute names, typically, we want those to be unique. Will it break anything if they're not unique in a database? No, it'll work fine. But to reduce the ambiguity, generally we recommend keeping all the attributes unique. One way you can do that is always prefix the attribute name with the name of the table in which it appears. So if you have last name in the employee table, instead of just having last name, you can have employee last name so that it's non-ambiguous. You know exactly what that attribute is. Primary keys can also be consistently named. So for example, if I have an employee table and I have a primary key, I might call it employee key. And if I have a department table, I might call it department key for the primary key. So you can keep those names consistent as well so that anytime you're looking at a list of attributes, it's easy for you to pick out which one is the primary key. Again, these are not required rules. They're just best practices. Foreign keys should also retain the same attribute name as the primary key to which it references. And we're going to use primary keys more later on in our physical design. One thing I want to note here too is generally we don't want to have spaces between our words. So if you have multiple words in an attribute name or in an entity name or anything for that matter, you generally don't want to have spaces in that, but it's also hard to read when there's no spaces. So if you take a look at employee key, that's two words put together. So one of the other conventions that's pretty common is to use uppercase letters to separate the words rather than a space. So instead of having employee space key, I have employee key, but the K is capitalized. And also notice that the E on the front is lowercase. Again, it's just a convention. It won't break anything if you don't use my conventions here, but these are pretty common conventions. In fact, the one I'm describing here for employee key is typically called the camelback notation. So you'll hear that called camelback notation because it's got the humps, right? You're reading the words and they have humps. And it is a pretty good way to write that out without the spaces. If you don't do the capitalization, it gets harder to read those, harder to see them. So it's a good idea. And again, these are all just conventions. They're not necessarily required. Once you finish the ER diagrams, a picture is worth 1,000 words. So it's a good idea to keep these around. You're going to use these ER diagrams when you do your physical design later on. So definitely keep these diagrams, keep them handy. You're going to use them as you go through the process. And it's always good to have these diagrams to go back to in a complicated design so you know why you made a certain design decision. So again, it's a good idea to keep them laying around so we can go back and reference them later on. So documentation is, of course, important. We're going to use them in physical design. We're going to use them when we do normalization. As we generate SQL code, we're going to go back and use these ER diagrams, whether it's a logical design or a physical design. So let's tie it all together. Here's all the tables I used in my examples. So when you create an ER diagram, it'll look something like this. You're going to have all your different entities. You're going to have and all your relationships between those entities. Not every entity relates to every entity. You can see here we have kind of two islands in this entity relationship diagram. You've got the book stuff on the left or on the right-hand side, and on that bottom left, we've got some employee stuff. So they're not directly related to one another. Notice too, I'm missing my primary key on some of these. In a good entity relationship diagram, you would of course have all of your primary keys identified. Since it's a logical ER diagram, you don't necessarily need to start thinking about the foreign keys yet. We're going to cover that in the physical design, and you also wouldn't have to worry about data types and things like that. So we'll talk about that stuff later on. So that's how we do a logical design using entity relationship diagrams.